Record. Hello. So for question 5.3, let's summarize our discussion. All right, let's start by reading the question. Determine V of t for t greater than 0 for the circuit shown in figure 14.51. So we're looking for the voltage across an inductor. I put this useful table for converting the elements from time domain to frequency domain using the Laplace transform or their equivalents. You can use it as a reference. But let's start. Our first step, if we have a circuit like this with a initial condition and a final condition, we can start by solving for the initial condition. So initially, we have a voltage source, resistance, and this gate is open, another resistance, and a capacitance which acts like an open source, and an inductance which acts like a short source, which acts like a short. So initially, since this is ground and all of the current is passing to the capacitor, the voltage across the capacitor will be equivalent to the voltage here, which is 7.2. So V C 0 negative equals 7.2 volt. Let's uh, let's write it in a better handwriting, keeping with the small text we are familiar with. So VC0 negative equals 7.2 volt. So that's the voltage across the capacitor. If you like as well, we can write the current across the inductor IC 0 negative is equals to, so the current passing here, it's a short, so it's equal to 0. All of the other initial conditions are 0. Let's convert the circuit to the S domain. So we check the circuit. Let's how to convert it to the S domain. So initially we have, it's converted to the S domain in the final condition. So after this gate is connected, all of my current passing coming from the source will go directly to the ground. None of it will pass here. So this part, so this will be my final condition, something like this. Let's get its equivalent S domain. So we have a resistance. We have a resistance of 73 ohm, remains 73 at S domain. We have a capacitance. So capacitance is 1 over SC, 1 over 2000 micro, which is 500 over S. Please check if you are solving. So 500 S. And we mentioned that a capacitor has an initial condition. As you can see, the capacitor converted to S domain is converted to a capacitance of 1 over SC with a voltage with V0 over S. So positive, negative. So 7.2. We mentioned our initial condition for the voltage is 7.2 over S volts. And finally, we have an inductor. Oh, sorry. We have an inductor of impedance of the inductor in S domain as 0.03 S. Yeah, 30 milli, so it's 0.03 S. And we are solving for V. We don't have a V source here in this circuit. So what would be the easiest equivalent? Let's write the equivalent KVL. So 73 times IS plus 500 over S times IS plus, so that plus 7.2 over S plus 0.03 S times IS. Solving for IS times 73 plus 500 over S plus 0.03 S equals negative 7.2 over S. So let's move everything to the other side. So IS equals negative 7.2 over S times 73 plus 500 over S plus 0.03 S. Yeah, let's convert the denominator and numerator in our usual polynomial shapes. Let's multiply top and bottom by S. So I of S equal negative 70, or before a better way, we are not solving for this circuit, we are not solving for I of S, we are solving for VS. VS. In that, as we mentioned earlier, VS equals IS times the impedance across the inductor times 0.03 S. Let's solve for VS. So VS equals negative 7.2 times 0.03 S over, so it should be times S, times 0.0 S, yeah, over S. We can cross the S with S, or 73 plus 500 over S plus 0.03 S. I mean, we shouldn't cross it to make it factorization easier. Let's multiply the S by all the elements. So negative 7.2 times 0.03 S over 0.03 S squared plus 73 S plus 500 takes the 0.03 outside. So equals, or we can from here directly solve in MATLAB, just factorize it, get the roots and everything, or let's just do it manually for now. Times 0.03 S over 0.03 times S squared plus 73 over 0.03 times S plus 500 over 0.03. So that's our VS. We can solve for the roots of the so the denominator will have two roots, so therefore we'll have two components, and we can follow the traditional method in solving, converting this using Laplace. I hope everybody's familiar with how to continue from here.